Hello, everyone. Welcome back. Sorry, we had some audio issues, but it seems like we have fixed them already. Again, let me just introduce myself again. My name is Rodrigo, and we're going to be doing a student project presentation today with Noor. He's going to be showing us his final project for the course ROS Basics, in which he is using topics, services, and actions, and he's using topics in order to publish to a velocity topic through in a Turtlebot 3 robot. He's going to be detecting the wall and stopping, and he's going to be using a service to do a square motion, and then he's going to be using an action server to record the odometry. So, hi Nor, welcome, and hopefully you're still ready to present after that little technical failure. So
Yeah,
how you doing?
I'm doing great. How are you doing, Rodrigo?
I'm good. I'm a little better now. Let me tell you that.
Well, I hope so. Um,
All right. Yeah. Now I've confirmed that your audio is working, and I want to thank the audience that was watching your stream, and because they let us know that it wasn't working. Thank you very much to the viewers, and so yeah, why don't you tell us a little bit about yourself, and we can get started with the presentation.
okay, fair enough. Well, my name is Noor Aldin Al Faris. I'm a mechatronics student at the Turkish German University. The reason why I'm interested in ROS because I believe that robotics should be very important in the future, and the robotics is the pure mechatronics, as they say. So, without any delays, I would like to share my screen and jump right to my project.
All right, we can see your screen. Well, hold on, just a sec.
Oh,
All right, we can see it now.
okay. So, first of all, I would like to go through the goal of each part before I explain my code. So, the first part, we have a requirement that to use topics and subscriber and publishers in order to control the Turtlebot robot to prevent it from collide with a wall or some kind of an obstacle. So let's jump right to the code. First of all, we have all of our imports here. We're going to use the laser scan to make the robot read and perceive the object, kind of perceive and understand the object around it. Twist is going to be used to publish the commands related to the velocity of the robot. Well, after that, I have my first function here. It serves only the purpose, which is to make sure that the message was really published once in the topic, uh, um, in the same devel topic, to be more specific. After that, I got my second function, which I named move. It will be used to pass two parameters to publish to CMD velocity topic, which are x for the linear velocity in x direction and yow for the angular velocity on z-axis. And these are pretty much all what we need to fully control the turtle, at least for this simple application. Well, the last function is the most important function. Well, it's a callback function for our subscriber for the laser scan or the scan topic. This means it should be called whenever a new laser reading is received from that topic. Uh, uh, um, First of all, we're going to take what matters for our application, which is the field of ranges. So ranges is not more than an array of proximity readings in which the index correspond to the angle in which as I said, the index correspond to the angle of the reading. So we are gonna just take the minimum reading of the middle, which is the minimum reading of the second third of the indexes, because it's correspond to the front side of the robot. After that, we're gonna make a decision, which is if this reading, if we have an obstacle within the range of 0.2, we're gonna stop the robot immediately. Otherwise, the robot gonna carry on and move forward with that velocity specified here. So I would like to jump to the real lab in order to test the code I've written here. Okay. I want just to make it a little bit, yeah, it's obvious now, I think. So let's ROS run our script.
So this is just the that program you just showed us, right? That's
yeah, exactly. So let's hit enter and see the what's gonna happen. So the robot moves forward until it detects a wall within the specified range, and it should stop.
Yeah.
So it worked just fine. Okay. Now let's talk a little bit about the second part. It's a little bit more complicated than the first, as expected. So in the second part, I think, yeah, here we're gonna use the service for such a goal here, as stated. The robot should move straight forward for 15 centimeter, stop and turn 90 degrees, move straight for 15 centimeter again, and repeat that to complete a square. If an obstacle found, stop the robot. Yeah, fair enough. Stop the robot, call the service, and send the error message. Fine. Well, let's have a look to the service server script I've written here. Okay. So first of all, we have the same functions actually. I've explained in the first part. The publish ones in the CMD-val, we're gonna use it again, and the move function. We're gonna have two callbacks. The first one is the callback of a subscriber to the scan readings. The only different here is we're gonna change the global value obstacle Boolean value and make it true if we got an obstacle with the same specified range. And after that, the robot should be stopped, actually. Well, the other callback function is the request for callback function for the surface. First of all, the obstacle should be declared as false, just to make sure that it's not affected by the previous call. And after that, the velocity should be specified here, and the angular velocity. The distance to be moved, actually, it's SI unit, so it should be transformed to meters, which is 0.15 meter. And the angle is pi divided by 2, which is 90 degrees, as specified in the requirements. Well, the time to be specified here, I call it the linear time factor. It's no more than the time that makes the robot will make that distance with such a velocity. It's just the famous kinematic equation. The time is equal to distance over the velocity, and it's just the same for the angular velocity. There's no difference here. The angle should be divided by the angular velocity, and for in range of 4, the 4 sides of our square, it should be moved with specified velocity forward, and we're gonna let this CMD-val until it's cut the specified distance, which is 0.15, and after that the same would be to make to make the robot turn around and rotate 90 degrees. After that, if everything went all right, we're gonna move the robot, and if there's no obstacle, we're gonna return true for completion. Otherwise, we're gonna let our log publish the error message and return false. Of course, we have here the obstacle variable should be permanently updated, and if we get an obstacle, the loop should be broken, and no more move should be done. Well, let's make two scenarios for this application, one with the obstacle and the other without the obstacle. Where is my, yeah, okay. So let's make the robot turn around in order to make it not encounter any obstacle for the first scenario. Okay, I think it's fine.
Yeah, that looks
And
like
let's jump to
it'll be
our okay. So I think I have launch file for this. So I'm gonna, well, I didn't talk about the client script because it's just straightforward. We're gonna just call the service from the ROS node.
right. Yes.
So there's no big deal.
And
Anyway,
we can go ahead and test
it's
the
called for the launch file. The launch file is will actually launch the server first, and after that it would launch the client to call for the service. Let's have a look here. Yeah, stopped somebody.
Yeah, I think there's an issue with the camera on the left, so you can sort of drag that to, if you want, drag it to the left, so we only.
Well, I'm gonna start again because
Yeah.
it wasn't so obvious. Okay.
There we go. Oh, there's a coworker. So this, in theory, is not going to run into an obstacle, correct?
Well, it's for some reason skipped the last slide anyway. Let's make it in front of some kind of obstacle in order to make sure that the error message was called and the robot is stopped.
Mm-hmm.
Something like this, I think, would be enough. Yeah, I think it's okay. So let's call it again. Well, it just stopped ROS successful. I may just make it a little bit closer to the obstacle, but we have got our error message here.
I can see that.
There were an obstacle. The service is interrupted.
Oh, that's really interesting. That's like an addition you
Okay,
made.
so let's just move forward for the last part of this presentation, which is about actions. Here, the goal of this part is actually to make a server that make a record for X, Y, and theta values from odometry topic, and to publish it as 0.32 to measure every second. Okay, as a feedback, the amount of meters that the robot has displaced is to be published, and when the robot has stopped from the front of the wall, it should return the entire list of recorded odometries. So I have here my action server here. Again, so first of all, we have created a class here for this action. Its name is self-explanatory, the odometer record class. We're gonna make the feedback and result objects just to use them later. Well, we're gonna have our current x for the position, current y, and the for the orientation we have theta as specified in the part, and we're gonna make the the velocity updated, just in order to make sure that the robot has begun and stopped, because it should be stopped actually and return a value when the robot is stopped in front of a wall. So we're gonna have a subscriber for the odometry. The only reason of this subscriber is only to update these values. So our current velocity is the twist of this odometry. Our current x is the position x of the odometry. It's the same for the epsilon. And when it comes to the orientation, I think I had to make a transform, because the orientation information is published as quaternion, and it's asked here for a theta. I thought it's asking for the yaw theta. So I've used the function order from quaternion from the TF model, and update the current theta as the yaw of this region. Well, this should be updated permanently and very fast. But the action server should publish this as feedback once a second, and as well as the record for the list of odometries. So here I have a success boolean if everything goes just all right and we have no preemption. And I've started here the temp list in order to append it whenever we got a new odometry reading, every second actually. And after that, I've started here a loop just to make sure that the robot is actually moving, and it's not just go and give us a result without, and the robot still there when the server is called. And after that, the final loop is to make sure that the robot has actually stopped. And after that, the list would be returned as a result. Well, let's talk a little bit about this loop. I think, yeah, here I have the x from the self current x that is being updated permanently from the subscription, the callback subscription of the odometry. The y is the same, and the angle. Well, we're gonna make a temporary object from point just to make just to load it from our information, and after that append it to our list. Of course, we're gonna publish the current total as displacement of the whole displacement of our robots from the Pythagoras rule, I think. After that, we're gonna publish the feedback, okay, and the sleep is the ratio which is required. So once a second, we have done this. Yeah. Well, if everything went all right and we have success, we're gonna just log in info that everything is all right, and we're gonna send it back to the client. The client of this service in this application would be just as the first part. The only difference is that the action server would be called before the action server would be called before after the robot start to move. So let's just make it before we are run out of time.
Yeah, we have just enough time.
Okay.
Okay, so we can see that it's starting now.
Check this out. Yeah, actually. think it should be here a false or something. I maybe wrote this down yesterday on my last test or something. Anyway. Okay, let's do it again.
Can you check if the odometry is being received?
Let me check this out. Okay. I think I ran out of time. Well, bad luck.
I think you might have until 59. Can you hear me, Noor? Noor, can you hear me?
I think I ran out of time, Rodrigo, because we just started a little bit late, maybe.
Yeah.
Are you saying something? I cannot hear you actually.
Yeah, I think there's but
No, I cannot.
you can. The
I
stream
can't
is
actually hear you.
working and people can hear me, but I don't think
I think it's something that has to be
you
has to do
can't.
with my headphone.
Because it looks
Yeah,
like.
now I hear you. Just go ahead.
Can you can't hear me?
Yeah, I can hear you.
Oh, you can hear me. Great. Yeah. So I thought you had. So you're disconnected now.
Yeah,
All
unfortunately.
right. Unfortunately, yeah, because we had some. I had some issues with the audio in the beginning. We ran out of time for our presentation. But you know what you can do is disconnect from the real RoboLab, and you could check in the simulation. You know, you can show us there.
Okay. Let me just copy the launch simulation. Okay. See or nothing. Okay. That's fine. Yeah.
You might have to zoom out in the beginning because.
Okay.
There you go.
Okay. So as I say, it's me again. So there's the commitment. Let's start. Okay.
I think because you see the spinning wheel on the top left,
Mhm.
bottom left, sorry. I think you have to close that terminal altogether and wait until that thing on the left stops spinning, which is where you open up a new terminal. That happens usually when you make the transition from being connected to disconnected. So actually, you might have to close Gazebo as well.
Okay. Just let me reload it.
Whoa. But anyways, this is the last part that records the odometry, correct? And if you want, I can start asking you questions about what I thought was really interesting.
Yeah. Okay. Go ahead.
And while this is loading, so is there any particular reason you divided? Oh, there you go. We're back up. So if you want, you can start launching everything. But let me ask you: is there any reason why you divided the scan in 3 sections as opposed to, let's say, 5 or 6, or it's just like an arbitrary number?
It's actually not arbitrary. From what I've experienced, there is a little bit difference between the simulation and the real robot. Maybe when it comes to reading, or maybe it's just something I've done it wrong at first.
No, you're correct.
So that's why I've divided it into 3 parts, just to make sure that the second third is what we are looking forward. Whatever the length or the precision of this.
The resolution of the scan.
Exactly. The resolution of this ranges
Mm-hmm.
So that's why I've done the middle to be the minimum reading of these ranges in the second third, from the second third to the I think from the first third to the second third.
Right, I understand.
That's why I've done it that way.
So now I think you can show us the last part if you still want to show us that on the simulation, because.
I think it should be working now. Let me open Gazebo. Okay. So let's launch this another time.
So what is inside of this launch file?
It's no more than the server. Check it out. Part 3. It's just the our server.
The action server and the
action client.
And the publisher. Okay.
Yeah, exactly. Okay. Let's see robots. Start to move.
So yeah, we can see it move.
And these
current location. Okay.
Feedback. Exactly. And lastly, you're gonna get the whole odometry
the whole message.
Yeah.
And that's one by one until it stopped. No.
Yeah.
Oh, and then you can kind of see that you were publishing sort of at, if you're doing that at one every second, it looks like it's moving 0.1 velocity. So you published at 0.1 for the command vel, correct?
Well, I think it's I am publishing it. Yeah, actually, yeah, it's correct.
Yeah, that's interesting.
Well, the odometry readings are not perfect as much as I understood. So it's not like the readings we've got from the gazebo position.
Yeah.
It has some kind of error. Uh,
Yeah, definitely. And the more it runs, the more the odometry will drift in the real robot. So let me ask you, because this actually relates to what we saw in the presentation before you. I see
mhm,
that in your action server for recording the how the robot is moved. You have
mhm.
section, and you've told me this, but I think it would be interesting because I thought it was a great solution on your part. Uh, that you were using instead of odometry, you have some commented section there that is using instead of the odometry topic, it's using the command vel topic. So can you
Actually,
explain a little bit on why you did that and how you thought about solving it?
yeah, sure. Actually, I've thought about it like unperfect um, Riemann sum. So I've tried to integrate the CMD val in order to get the odometry values. The reason I prepared this solution because as you said before, the odometry was not working as expected. So I've tried to make my own solution on this. It actually, but it has limitation is that the CMD val should be published in it should be updated so fast in order to get a precise
Yeah.
solution. So first of all, I've defined here a refresh rate in order to just to multiply it with the velocity to make this dx, or it's not dx in this file, it's delta x. And after that, I've summed this delta x to the self current x, our current x movement. I think I could show you the entire thing now, maybe.
I mean, yeah, if you want, we there's no rush, and I think it's a really interesting solution that you came up with, and it really shows how well you are familiarized with this, and it's just really impressive there.
Well, here we have calculated the delta x in which we make our velocity, our self current velocity. It would be updated, as I said, this callback function. So we have our current linear velocity from linear x, and we're gonna multiply it with the current theta in order just to get the component in x direction.
Hmm.
And after that, we're gonna make the component of the velocity. So we're gonna just multiply it with the refresh rate of the time in order to get the unperfect, or just let's say it's unperfect Riemann sum. Because we actually don't have the function that the Turtlebot will move according to.
Hmm.
We have to just calculate the integration of it in discrete manner. So we're gonna multiply it with refresh rate, which is as much as it's small, it would be perfect for it. Because the perfect way of it, it's
Infinitely
infinitely,
small, yeah.
yeah, exactly.
Wow. So you
So,
turned sort of a yeah. I love that you are trying to do it as discrete as possible in order to get the most accurate
exactly.
value there.
So after that, we do the same with the y to calculate the delta y from the previous reading. And after that, we're gonna just add them together just to get the current x and the current epsilon, the current y. The theta is the same actually. We're gonna just calculate the velocity and multiply it with the refresh rate of our. After that, we just have to make sure that this whole thing is updatable just in the rate that we have specified, and just not more just more fast or something like that. That's why we're gonna make it sleep for the specified refresh rate. So as I said, it has a limitation that the CMD val should be published very quickly, and it should be updated very quickly. in order just to get the current reading and not something else.
Yeah, I think right now it's published at um,
Uh, Actually, in our application, yeah. But when it comes to using the that pad stuff in order to move the robot,
mhm.
it's just I tested actually just in order to make sure that the result of it is as precise as acceptable. So when we use the that thing in the real robot, it just actually published the CMD once. That's why we
Mm,
the
mm.
result that we've got here is actually ridiculous. But it's actually pretty good for this application because the CMD value from the publisher actually is published just in very high rates.
Right. Yeah, yeah, yeah.
So yeah, that's what I've done as a solution if the odometry is not actually working.
That's
So
really clever and really impressive. I like
thank
that.
you.
I like that.
So we just look this bell for the specified variable, and let's change this subscriber from odometry to our CMD bell. Well, I think it should be well.
Let's
Let's
see.
let's call the reset word in order to. I think I've never stopped this image mapping. So still publishing.
Yeah,
So
yeah. I like that you already know exactly the name of the service.
okay. So let's do it again. So it's moving now, and we should be getting our yeah. Of course, this is not due to some kind of origin. It's just from the beginning of the
Yeah, yeah, yeah. But I mean,
design.
it looks like it works really well. It's like,
Well, actually, I've tested. Yeah, it's just fine. It works just acceptable. I think.
yeah, more than acceptable. So there you go, guys. Like, if a way to record the odometry without the odometry. I think that's really impressive.
Thank you. I'm glad that this come to you like.
um, so I'm trying to think of what other questions, but that's pretty much it from my side. So, is there anything else you want to let us know, to, show us in your project, or?
Well, actually, I just want to say that project was so good in a manner of measuring the how much students have grasped the concepts of application services and action lives. It's just so challenging, but it's not too difficult for a new student to achieve it. So I think it's pretty good project. So thank you.
I'm really glad to hear that. Do you mind stop sharing your screen so we can?
Yeah, sure.
Oh, there it is. So I'm really glad you say that because that's sort of our goal is to do it as practical as possible, but like as accessible as possible, but still challenging the students. So um, I'm really glad that you say that, and let me just say thank you very much for presenting. Again, I'm sorry about the couple of technical issues that we had, and that unfortunately we ran out of time there at the end with the robot. But great job, Noor. I thought it was a really good job.
Well, thank you, Rodrigo. I think so. Never mind about that problem. I just it just was good, I think. And thank you for the great academy.
No problem. I hope you continue on to other courses if you're still trying to learn more things, or just apply what you've learned to your personal projects or your school or your work. And this is for everyone that will be watching this. This is what you can do here if you take this basics course with us. You can uh, implement your learnings in a practical manner, and you can test your programs in a real robot, and you can present and show everyone what you've learned. So now it's up to you guys to do the same here as Noor. And you did a tremendous job, Noor, and hopefully we'll see more of your projects in the future.
Thank you, Agrip. I hope that's so.
Well, that's it from us, guys. So we'll see you for the next presentation, and I hope you enjoyed this. And bye bye, guys. All right, ended.